To build a Gauss rifle, you'll need 2 rulers, tape, scissors, magnets, steel balls, roughly the same size as the magnets. The finished setup should look like this. Our setup uses 2 rulers as rails, 4 pairs of magnets, each spaced 2.5 inches apart. On the same side of each pair of magnets, place 2 steel balls as shown in the video. Using your last steel ball, push the ball towards one of the magnets as demonstrated in the video to start the Gauss rifle. Let's show that demonstration one more time in slow motion. Whoa! What just happened? Okay, that wasn't some crazy magic, but instead, there's some physics behind the Gauss rifle.
The ball is given an initial velocity v0. As the ball moves towards the magnet, it experiences a magnetic force due to its ferromagnetic properties. This is important because the ball must transfer enough energy to the third ball to escape the magnetic force of the magnet and accelerate to the next state. Before the collision, the ball accelerates from its initial velocity to velocity v1. When the ball finally collides with the magnet, it experiences an impulse due to the contact force. The equation for impulse is the integral of force with respect to time. Impulse is also equal to change in momentum. And because momentum is conserved, the system experiences a change in momentum of equal magnitude as the impulse is transferred throughout the system. The magnet is taped in place, and the ball closest to the magnet is stuck due to the strong magnetic force. So ideally, the magnet and second ball don't move. So all the momentum is transferred to the third ball. With each stage, the balls transfer energy and continue to accelerate due to the magnetic force. The balls continue to gain velocity, so the final velocity is therefore greater than the initial velocity. As a result, the final kinetic energy is greater than the initial kinetic energy. While it may seem that energy is not conserved, energy is in fact still conserved due to a decrease in the internal magnetic potential energy of the magnet, even though we cannot see it.
Here's our velocity time graph of the 5 balls as they move through the rifle. Ideally, we should get an increasing stepwise function because each ball has more kinetic energy than the previous one. We see this general trend in our graph. However, ball 4 shows a slight error in the way we made our Gauss rifle. It appears to have less energy than ball 3. This might be the case because the magnets weren't taped down strongly, so energy was lost as some of it was transferred to the magnet. An interesting thing to note is that each step has a U-shaped curve. This is because the magnetic force obeys the inverse square law. The magnitude of the force is inversely proportional to the square of the distance. As the ball leaves the magnet, it experiences a net force in the negative direction, because the magnetic force from the magnet behind it is stronger. But as the ball moves away from the magnet, that force decreases. The ball's speed decreases at a decreasing rate, explaining the downward part of the U. Soon, the ball reaches a point where the magnetic forces are equal, the bottom of the U. As it continues to move from this point, the magnetic force from the next stage is greater. That force increases as the ball continues to move closer to the next stage. The ball is accelerating at an increasing rate. This explains the upward part of the U. We should also note that friction is always acting on the system. The last ball looks like it has a constant negative acceleration.